String theory is a theoretical framework in physics that attempts to reconcile quantum mechanics and general relativity. It proposes that the fundamental building blocks of the universe are not point-like particles, as assumed in traditional particle physics, but rather tiny, one-dimensional strings. These strings can vibrate at different frequencies, and these vibrations give rise to the various particles observed in nature. String theory originated in the late 1960s when physicists Leonard Susskind, Holger Beck-Nielsen, and Gabriele Veneziano independently discovered the Veneziano amplitude, a mathematical expression that later became a key element in the development of string theory. The first version of string theory, known as bosonic string theory, was developed in 1970. It described only bosons, force-carrying particles, and lacked fermions, which are building blocks of matter. To incorporate fermions into string theory, physicists introduced supersymmetry in 1971. This extension aimed to unify particles with different spin quantum numbers, but it required extra dimensions. The first superstring revolution occurred in 1984 when physicists Michael Green and John Schwartz discovered anomaly cancellations, boosting confidence in the viability of string theory. This led to the formulation of superstring theory. By the mid-1980s, 5 distinct superstring theories emerged: Type 1, Type IIa, Type IIb, heterotic SO, 32, and heterotic E8 times E8. This proliferation led to the term string theory landscape. Physicist Edward Witten proposed M-theory in 1995, attempting to unify the 5 superstring theories. M-theory introduced the concept of 11-dimensional spacetime and included membranes as fundamental objects. Discoveries of dualities, such as T-duality and S-duality, revealed the interconnected nature of seemingly different string theories. The introduction of D-branes, extended objects on which strings can end, provided a new perspective on the theory. Juan Meldacena proposed the ADS/CFT correspondence in 1997, establishing a mathematical relationship between string theory in anti-de Sitter, ADS, space and certain conformal field theories, CFT, without gravity. This duality has provided insights into the nature of spacetime. String theory has yet to make definitive experimental predictions and faces challenges in experimental verification. However, it continues to be a theoretical framework of interest, contributing to discussions about the fundamental nature of the universe. The concept of the string theory landscape suggests that there may be an enormous number of possible vacuum states, each corresponding to a different universe with its own physical laws. This idea has led to discussions about the multiverse within the context of string theory.